So this is the third and final video on nodal analysis. As you can notice, I've already labeled all my resistors and voltages, and I've already labeled the reference node. What I'm going to do now is I'm going to identify the nodes. So I know I have a node here, which is A, and then this top one is going to be one giant node. Like I said before, we can connect all three of these points. We'll just call this node B, and we have a node right here. Generally, if you're having a hard time deciding nodes, if there is a resistor, put a node before it and after it. And then this node down here is going to be the ground node, so we don't really need to know labeled that. Okay, so what we're going to do now is we're going to start at point A, and we're going to see that there's going to be a constraining equation between point A and C. So A is going to be A, the symbol by A, so that's positive A, and then minus, from that symbol, C. And that's going to be equal to the voltage between them, which is 12 volts. Now for the B, as you can notice, it goes straight down on this wire. It hits the 6 volts, keeps going, and it goes right down to ground. So B is actually going to be equal to the 6 volts. Since A and C are actually a supernode and share a voltage between them, we can actually combine both of their nodal analyses. So first we're going to do A. So we're going to do A minus the voltage through resistor 2. So minus 0, since ground's on the other end, over 2. And that's going to be plus A over resistor 1 minus voltage B. And like I said, we're going to go ahead and add the A and the C nodal together. So we're just going to go right onto the C now, and we kind of ignore this middle thing where they're connected for a little bit, because we've already gotten a constraining equation for that. So now we do C over the 1 resistor minus the voltage on the other end, which is going to be ground, so we can just put 0 there. So C minus 0 over that resistor. And then we're going to move on to the other wire, so we have plus C over that resistor 2 minus the voltage on the other end, which is going to be B. And that's going to be all equal to 0. So now we've already got the voltages determined at AC. So let's move on to solving for the voltages altogether. So let's just go ahead and simplify this one. So we can multiply everything by 2 in order to get rid of these fractions, because I really don't like fractions, so I like to get rid of them as soon as I can. So get everything and multiply it by 2. Now we're going to have A plus 2A minus 2B plus 2C plus C minus B is equal to 0. We can just go ahead and kind of combine all like terms. So we're going to have 3A minus 3B plus 3C is equal to 0. Now later on we're going to have to plug these into our matrix to solve for them, which I can kind of show you how to do in another video if you don't know how to do that already. So this is going to be one equation. For the next equation we're going to have our B is equal to 6 volts. So we're going to have 0A minus or plus 1B plus 0C is equal to 6. And then for the other equation, we're going to have the A minus C is equal to 12 volts. So we have 1A plus 0B minus 1C is equal to 12. Now if we plug this into a matrix, we would want it to look like this with none of the A's or B's or C's in it, but kind of like have little placeholders for them. So the first one's going to be represented by A, the second one by B, and the third by C. The last number is going to be represented by the number on the other side of the equal sign. So we're going to have 1, 0, negative 1, 12. And then we're going to have 3, negative 3, 3, 0, and 0, 1, 0, 6. If we plug this into MATLAB into our calculators as a matrix, we can hit reduce row echelon form, which you should have learned in linear algebra. And then you just put the name of that matrix. We could call that matrix M. And it will tell you what it is equal to for each of those. And that is all I'm going to go over for this video.